In this video, we're gonna go through the solution to the finite square well, which is sort of an extension of the infinite square well that we covered in the last video. So for finite square well potential, we have something very similar to the infinite square well, except for outside of the well where the potential is zero, the potential rises to some value V naught instead of infinity. This is slightly more realistic of a model where, if you think of an atom, some electron bound to a nucleus, it's going to have bound states that will exist and stay inside this classically allowed region. But if you give it enough energy, eventually that electron will be able to escape from that atom and ionize and into some unbound state. So the potential for the finite square well is written here. We have a length of a well equal to 2 times whatever constant A. So it goes from negative A to A. And we'll call this region 1, that where X is less than A, we have the potential V naught. Where X is greater than positive A, again, V naught. And in between, in the well, we have a potential of 0. Now, what our goal is, again, just to remind you, is to solve the energy eigenvalue equation, which in the position representation looks like this, where we have the energy eigenfunctions and the energy eigenvalue EI. Now, this is a piecewise sort of potential, so we're going to solve it in different regions. In this left region, we'll call it region 1, where X is less than negative A. Our potential is V naught, so we plug that in to our energy eigenvalue equation, and we get this. If we leave the derivative, the second derivative on the left and bring everything else to the right, we end up with this equation where we have negative h bar over 2m. The second derivative of our wave function is equal to the energy of the eigenenergy of that state minus whatever that potential value is times that energy eigenfunction. We can simplify this just like we did with or similar to what we did with the infinite square well potential. And this can be rewritten as the second derivative of our eigenfunction is equal to some constant squared times our eigenfunction, where we've defined that constant Q to be this. We've brought the negative from over here inside this bracket, so it's now V naught minus E. And what we're looking for in our solutions right now is we're considering the bound states. We want to know the eigenenergy and eigenfunctions for those bound states. So this is where the E, the energy of that eigenfunction, is going to be less than V naught. So this is a real number. This V naught minus E is a positive number, so Q is real. This solution, this differential equation, has a solution that's an exponential, but not an imaginary one previously like we had in the infinite well, but just these two exponential functions. And we can see that, if we take the first derivative with respect to x, we get this, the q and the negative q just come out in front. Do it again, and we end up with q squared times that original function that we started with. So we know that that is the solution to our energy eigenvalue equation. That gives us the form of the eigenfunction in region 1, right? If we move on to region 2, well, this is exactly the same as what we saw with the infinite square well. We have a potential that's equal to 0. When we plug it in, our eigenvalue equation looks like this. The exact same thing we had for the infinite square well. So we have a solution of the exact same form, that sine and cosine, the sum of a sine and a cosine, where we've defined this wave vector k just to be 2m e all square rooted over h bar. So we already went through the details of showing this in the previous video. I'm not going to repeat it here, but that's the gist. Again, we're going to have multiple constants here, so I'm just, rather than a and b like it was in the last video, we're calling them c and d. If we go to region 3, again, the potential is the same as it was in region 1. So when we plug it in, this is the exact same differential equation we had for region 1. The solution is going to be the exact same form. Again, I'm just using two different constants because so far, we might suspect that they should be the same, but we have no reason to say that right now. So Putting those all together, we have the solutions to the energy eigenvalue, the eigenfunctions of this form in those three regions. And I'm going to give them subscript 1 for the wave function in region 1, 2 for the wave function in region 2, and 3 for the wave function in region 3. But these are the forms of those solutions. To get the full solutions, we're going to need to know what those constants A, B, C, D, E, and F are. And to do that, just like we did with the infinite square well, we're going to have to look at boundary conditions. And the first one that we saw, that we used last time as well, is that the wave functions have to be continuous. So that means at these boundaries, at this boundary at negative A, the wave function from region 1 has to meet the wave function for region 2. Likewise, here, the wave function from region 2 has to meet the wave function for region 3. Another boundary condition we have is that the derivatives, the slopes, must also be continuous. We didn't have this in the infinite well case because it turns out that this isn't a requirement when we have infinite potentials. Infinities do weird things, but the gist is if this isn't continuous, we're going to have infinite energies in that. But if we have an infinite potential, we kind of get away with it. So, but for realistic systems without infinite potentials, the derivative of this wave function must also be continuous. So the slopes, if we take the derivative of these with respect to x and look at them at the boundaries a and negative a, they must also be continuous. A third thing we have to consider is that these wave functions must be normalized, right? So again, this comes from the fact that the probability, if we were to measure this particle at a given x, if we add up the probability of measuring it over all x's, the probability has to be 1, right? That particle exists somewhere. So if we add up all the probabilities, we have to be 1. And if we look at that, that actually tells us that this b and this e are both equal to 0. And we can see that if we actually look at the normalization condition. If we integrate the complex conjugate over times the complex conjugate of the wave function times the wave function over all space, that has to be equal to 1. That's the normalization condition. This can't happen unless b and e are 0. And you can see that because if we look at e to the negative qx, this term here, as x goes to negative infinity, where this applies, that term goes to infinity. So if we're adding up, the area under that curve, the only way that that's going to be non-zero is if this b is actually 0. Likewise, if we go over here to region 3, as x goes to infinity, this term's going to blow up to infinity, so e has to go to 0. You can think of this almost as the wave functions have to go to 0 at infinity. Otherwise, you're not going to be able to normalize these. Right. Moving on to the other boundary conditions, though, to solve for the other constants, one thing we're going to do here that's going to make things a lot more straightforward is we're going to look at some symmetry in this problem, right? So if you look at this potential, we notice that it is symmetric about 0, or it's an even potential, right? V of x is equal to V of negative x, right? Turns out that makes the differential equations, symmetric, have the same sort of symmetry. And that means, and we can show this in our synchronous meetings if you like, that the solutions, the eigenvalues, can be split into two types, odd or even. And we can actually create all those solutions from odd and even solutions. So we can look at the even or odd types separately. So if we start with the even solutions, that sign term in that region 2 goes away. That's an odd term, right? So we consider only the even parts of these wave functions and look at the solutions and impose the boundary conditions. So the first boundary condition, if we look at the left side of the well where x is equal to negative a, we know that wave function must be continuous. So the wave function from region 1 when it gets to negative a must meet the wave function from region 2 when it gets to negative a. If we plug that in, we get a times e q to the negative a has to equal d cosine negative ka. And since cosine's even, that's the same as d times cosine a. Likewise, the derivative of those functions have to be the same at that point. And if we take those derivatives, we get this. We get QA times e to the negative QA is equal to negative KD sine of negative KA. Now, since sine's odd, sine of negative x is equal to negative sine x, so there's going to be a negative sign. The negative signs are going to go away, and we have that equation. Turns out if we look at the boundary at x equal to a and impose those boundary conditions, we're going to get very similar equations, right? F is equal to negative QA, and just plug in a into those variables, into those functions, and that's what we get. And likewise, if you plug in a into the derivatives of those functions, we get very similar equations. Now, one thing we can notice here, because all we've sort of done is create the equations from those boundary conditions. Turns out these two equations, the wave function being continuous at both those boundaries, we have d cos Ka and d cos Ka, both equal to this, and that means that a e to the negative qa is equal to f e to the negative qa, or a is equal to f, right? So as we suspected, region 1 and region 3 are going to have those same constants, or the constants of those terms are going to be equal. Another thing we notice, though, now that we have this a is equal to f, we see that these two equations are actually the same equation, and likewise, the equation from the second boundary condition is also equivalent, right? We probably should have expected this. If we're looking at even solutions, a boundary at positive x is going to give us the same equations as a boundary at negative x, or a, I guess, is what we've been using. But anyway, those two equations are this. We have our solution now with a substituting a for f because they're equal. Our even solutions for our energy eigenfunctions are this, and we have these two equations, right? And it seems like we have two equations with well, let's say 4 unknowns: a, d, k, and q, right? But we get turns out k and q are really only one unknown because they're both related to the energy, right? So q, if you recall, was this, so this energy, it's related to energy, and k is equal to this, so it's also related to that energy. So those k and q are really one unknown. So we have two equations and 3 unknowns: a, d, and the energy eigenvalue for this eigenfunction. We get a third equation from the normalization condition when we impose that. It's tedious. We're not going to go through the details, but it's pretty straightforward doing that integral that we showed earlier and setting it equal to 1. Can get you that. Here, what we're more interested in is figuring out the energy eigenvalues. And we can do that to get there is just take this second equation here and divide it by the first equation here, and we end up with this, right? These two terms cancel, and we have q is equal to k sine ka divided by cos ka, or just k tan ka. So that's our even solutions. Unfortunately, we don't have an analytical way. Like I can't solve this analytically. That's just going to give me those things. So we have to sort of do it numerically or graphically. And one thing, so we're going to go through a graphical solution now to show you kind of the idea of how this works. And one thing that's going to be very useful is just multiply both sides of that equation by a and define some constants, right? We're going to define this variable z, which is equal to the wave vector k times a, equal to that, just substituting what k is equal to. This is sort of, this z sort of parameterizes the energy of the eigenfunction that we're looking at, right? Larger energy, larger z, smaller energy, smaller z. All the other things are either constants or properties of the well that are constant. Z naught is sort of parameterizes the well size, right? The depth v, and even the width a, right? If we're looking at a very large or very deep well with a large potential, and that's very wide, we're going to have a very large Z naught. Likewise, if either of these get smaller, we're going to have a small Z naught. And why do we do this? Well, we can look at this. If we look at Z naught squared minus Z squared, right, and just plug in things we get here, we have 2m v naught over h bar squared a squared. Just plug in those values and we get that difference. If we do that, we can factor out this 2m h bar squared and the a squared to get this term here. And that's how we defined our q, right? So this is, sorry, q squared. So this is equal to q squared a squared. So by making these substitutions or defining these variables, we can see that z naught squared minus z squared is equal to q squared a squared, or written, taking that back here, qa is equal to the square root of this, and that's equal to z tan of z, right? So this is sort of the equation we're going to solve. And if we can figure out the z that solves that equation, we've figured out the energy that the energies of that eigenfunction. So our strategy is going to be plot the left-hand side and the right-hand side and see where they intercept. Where they intercept are the z's or the z's that satisfy this equation. So what I've shown here, this is just a plot. That is, a circle essentially of radius z naught, and it is shown right there. And z tan of z are those black lines, right? And the solutions are given by where they intersect. So you can plot this really accurately and look at it, or solve it numerically, however you wish. But those intersections give us the from there we can pull off the solutions, the z's that satisfy this equation. We've only been looking at the even solutions to the energy eigenvalue equation. Turns out we're not going to go through the details because it mirrors exactly what we just went through. It'll probably be on the homework. But if you look at the odd solutions, you get this equation. Z naught squared minus z squared is equal to negative z, the cotangent of z, which are these red lines on this plot here. So what you can see is, I think I've used, just for making the plot, a z naught of 5. Yeah, that's exactly what I've used. You can see because that's the intercept. We see that there's going to be solutions for the even ones too, but we have 4 solutions, where it intercepts the 2 even functions and where it intercepts the odd functions. That gives us, we figure out what those interceptions, where the z value, where those intercepts occur at, and we get the energy, the possible energies, the energy eigenvalues for this equation. And you can see they're quantized, 1, 2, 3, 4 in this case, right? Again, we get the constants A and D from looking at the normalization. But putting it all together, this is what they look like. We would have, here are the solutions to that equation, and the wave functions look like this. We have a cosine, the even terms, with different wavelengths, sort of just like we had in the infinite potential well, but we actually have some penetration into the barriers here that are those exponential decaying terms, right? And we'll discuss that more in the next video as well, but we see that there. And then we have the odd functions, the sine solutions, of different wavelengths, again, with these exponential decaying terms in the potential. And one thing you notice is we have a finite number of bound states. In this case, what's drawn here, which is from the textbook, there's only 4 states. But if we were to make this potential larger, we would end up having more bound states. If we made it smaller, eventually this state would be higher energy than V naught, and we would it would no longer be a bound state. The solution wouldn't be an eigenvalue anymore. So if we make the well deeper or wider, we're going to have more bound states. You can also see this from how we got our solutions there, that graphical representation, right? So we have the same solutions drawn here, that the even tangent times z terms, and then the z times cotangent terms here. And this z naught equal to 5, so large potential and width, gives us this blue line here, and we see we have 4 solutions. If I make it smaller, just make it 3.5 here, I have that z naught squared minus z squared, all square rooted, gives us a smaller radius circle, and it only has 3 solutions. If I continue to make it even smaller, I'm only going to have 2 solutions, and then eventually just 1. So this is, kind of what you might expect. As I lower this um, well, the depth of the well, I'm going to end up having less and less bound states in this system. If I make it larger and larger, if eventually I go to infinite, I'm going to have an infinite number of solutions, just like I did with the infinite potential well. And again, we're going to have in the next video, we're going to sort of discuss these two square wells, the infinite and finite square well, and sort of just conceptually go through how to think about them and some of the things we've learned. Um, in that, I will also mention one more thing. No matter how small we make this well, provided there is a well, there will always be at least one bound state, right? As I make this plot smaller and smaller and smaller, there's always going to be some intersection with this first curve here. So there will always be one bound state in any square well. And it turns out for any potential well, there will always be at least one state. Anyway, we'll discuss more about these sort of features of this in the next video, where we'll compare finite square well and the infinite square well, and just make some comments on how they work, and actually move into time dependence. Now that we have the energy eigenvalues, remember that is what went into Schrodinger's equation, right? We had the energy eigenbases and those energy dependent phase factors that determined the time evolution of our system. So we're going to get into that.